Congratulations.
Thank you.
I am the person.
Okay, last topic we are covering, and we are just going to do a brief one, not even really doing the full section here. Talking about polar form for complex numbers. All right, so we are used to dealing with like an XY coordinate grid, okay? But and every time we've talked about imaginary numbers,
XYZ?
I wish. I know. We don't get to that. Calc 3, you get to XY. So, every time we talked about imaginary numbers, I've told you, well, we can't graph those on our standard XY plane. But if we have the imaginary plane, we can graph them. So if we're graphing a complex number, so something of the form a plus bi, your horizontal axis, so what we're typically thinking of as our x-axis, turns into the real axis. And the vertical, instead of being the y, becomes the imaginary axis. So instead of having an x and a y axis, we have a real and an imaginary.
That's XYZ. You gotta go count 3 for that. I've just been informed.
Practice. I want to find the sum of these two imaginary numbers, 6 minus 2i and negative 4 minus 3i. Then we'll graph both complex numbers and their resultant, which is what it's called when you add them together. So first, the resultant. If we just add those, how do we add complex numbers?
Just put the legs with the legs.
Okay, so 6 plus negative 4 is 2, negative 2i, negative 3i, negative 5i. Okay, if I'm going to graph all of those. So 6 minus 2i. You graph the real, so that's 6.
Second order.
The imaginary is negative 2, but then you actually graph them like vectors. So it's not a point, it's like a vector going to that point. Pretend that line was a little more straight than it looks.
That's okay, mine's the same way.
If I asked you to graph negative 4 minus 3i, so we go left 4, we go down 3, so we graph the real, then we graph the imaginary, and then we draw it as a vector, ending at that point. The resultant is what we get when we add those two together, and we got positive 2, negative 5i. And you notice that is right in the middle of them. If I drew straight lines.
Just make it bigger.
Yeah. Isn't that how you fix it?
That's how I do it.
So we just graph complex numbers and the resultant. There's.
Did you imagine getting a grape? Like, I couldn't imagine buying grapes. I didn't know they did grapes by weight, and one day I went in and I was like, oh, I'm just gonna buy like $3 worth of grapes. I thought that was just a bag of grapes.
Okay. The next piece. Talking about x, y, r, and theta. We have seen all of these variables represented a couple different ways so far. We've seen them back in the first week of trig when we defined our trig functions. We had x, y, and we had r. We had talked about this Friday when we were talking about our vectors. So we've seen it a couple different ways. Remember, if I'm talking about x, that's our horizontal. Y is the vertical. Where's r? Yeah, it's like our hypotenuse.
Oh,
This is my theta, if you're going back to like our SOHCAHTOA, the first time we had it. So a couple things to remember. In a right triangle, x squared plus y squared equals r squared. So r is the square root of x squared plus y squared, so we know that. When Friday, when we were talking about how to find that angle, if you had x and y would be which trig function?
Oh,
Yeah, you could do tangent or cotangent. I said tangent, but Tangent is y over x, so those are things that we know. Friday, I gave you formulas for like your horizontal and vertical components for the x and the y. But it's really just related to our trig functions. If I were looking at x and r, adjacent and hypotenuse, that means cosine of theta equals x over r. So if you solve that, x is r times the cosine of theta. So that's what that horizontal component was when we were writing the vector on Friday. The vertical component when we had to write the vector. We're looking for y. Sine, opposite over hypotenuse, is y over r. So y is r sine theta. So those formulas I gave you for x and y, they weren't different than what we'd already used. We were just multiplying things over, solving them. Is that okay? So when we talk about what is called polar form of a complex number, so it is defined to be r times cosine theta plus I sine theta. Okay, and here's why. Here's our explanation. If I give you a complex number, like 6 minus 5i, when you graph it, the 6 is your real number, right? And we put that on the x-axis. Okay, so based on our previous slide, we said x is r cosine theta. So 6 is like our x, which is the r cosine theta. The negative 5, we graph that on the imaginary axis, which is like the y, and y is r sine theta. So if you're thinking of it as like an ordered pair, an x and a y, they both have r, so that's where the r out in front comes from. And then you have the cosine, the sine, and the I just comes from the fact that it's an imaginary number. Okay, so that's just kind of a little justification on why this form is what it is. All we are really going to do is practice going back and forth between rectangular form, which is what we typically are used to, like our ordered pairs, and the polar form. So if I said, here's a polar coordinate, and I want to write that in rectangular form. That's like what we're used to, how we typically see our complex numbers in standard form. So a plus bi is what I need. So that means polar form has trig functions, rectangular does not. So what would I have to do here? Yeah, evaluate sine and cosine. What quadrant is 300 degrees in? 4. Reference angle is 60. Okay. In quadrant 4, is cosine positive or negative? Positive. What's the cosine of 60? Plus I times, okay, in quadrant 4, is sine positive or negative? Alright. So if we distribute, 2 times a half is 1. Negative radical 3 over 2 times I times 2 would be negative I radical 3. That's my rectangular form. So if you have polar and you want rectangular, all you have to do is evaluate your sine and cosine.
So does that 2, where is that 2 going on? Is it going on the fraction or the I, or does it matter?
So this is like 2 times 1/2 minus I radical 3 over 2.
Okay.
So then you take it to both terms. Other questions? So, it's a little bit harder if we're going the other way. if we have our typical standard form a plus bi, and I need to write it in polar form, because that means we have to have an angle, and we have to do our trig functions. So the first thing we are going to do is sketch a graph of the x plus yi. So graph the imaginary number. Then we will find r, which, when we talked about vectors, what was that another name for that side?
Magnitude.
The magnitude. And then we find theta, which we called our direction angle when we were doing our vectors. So that's kind of why we had that little lesson on vectors. When we find theta, we do need to be careful about our quadrant, which is why we have the picture. Let's get this.
Oh, we could do this.
All right.
First went from oh no to really confident. I don't know how I feel about that.
So is trigonometric form just polar form?
Yes. So trigonometric and polar are the same. They involve the trig functions. All right. So first, we're going to draw a picture. That way we know what quadrant we're working with. If you're graphing this, my real number is negative radical 3. So that would go to the left, like negative 1.7-ish.
Yeah.
This is like a 1i, so we would go up 1. So we know we are in quadrant 2. If I am trying to find r, you can think to your formulas, you can think to your picture. This is just like, this side is a negative radical 3, this is a 1, r is the hypotenuse. So this is something we've done all semester long. How do we find r?
A squared plus b squared equals c squared.
Mm-hmm.
Oh, so that's on 4.
That was our I, and I was a just by itself. So when we graph the imaginaries, remember I was the coefficient.
Oh, it is 2, right. Yeah, square root that, that'd be what?
So R is square root of 4, which is 2. All right, now we need our angle. So this was what we called our magnitude last week. Yes.
But whenever you're reading the imaginary number, do you not like read the negative one at all?
The negative 1 was on the radical.
I is not a negative 1 unless it's
Yeah.
squared.
This is just like a
No,
1.
I mean like the root negative one.
No, we just read it as the I. So we
Oh, we
disregard it.
only read it as one?
Yeah, so when we graph it, we're graphing the coefficient of I.
Okay.
So our angle is right there. So tangent is opposite over adjacent, or negative radical 3 over 3. Okay. Reference angle. When is tangent radical 3 over 3? We're in radians.
60 radical 3 over 3. That's not what we have hands for.
Or is it?
Oh, it's just 60 degrees. Okay.
60 is radical 3. 30 is radical 3 over 3. So it's like square root of 1 over the square root of 3.
Yes, but this is mine.
Yeah, that's your 60 here. So this would be I over 6, which is the same as 30 degrees. That's our reference angle. But we're in quadrant 2, so what would my angle be?
5 pi over 6. But
Okay,
it's negative because it's
the negative.
angles,
Yeah.
right.
Alright, so now the trig form, or the polar form, is just r parenthesis cosine of theta plus I sine of theta. And that's from the formula we wrote down for what polar form is defined to be. Think about, like on your unit circle, cosine is the x, sine is your y. So we have the x plus I times the y.
I don't know why I wanted to go back and work it out.
So that's a 1,
Which one?
negative 3 on it.
He's looking at the next one.
Okay, are we okay on part A? Alright, so let's talk about part B. If we wanted to be in in polar form or trig form, that's r cosine theta plus I sine theta. So we need r and we need theta. Okay, so if you start with your picture, negative 3i, that's the same as 0 minus 3i. So my real part is 0, my imaginary is negative 3. So we're just talking about this vector here.
So 0 degree 270?
So, yep, r is the square root of x squared plus y squared. So square root of 9, or 3. Our angle, we can see here, it lies on the axis. That is 270 degrees. So it's r cosine of theta plus I sine of theta.
How did they just like find this?
That just all depends on what kind of math you're doing. If it's more convenient to have trig functions or our standard x and y's like we're used to.
No.
I mean, to us, because we're used to it, it's obviously easier to have the rectangular form because that's how we always deal with things.
No,
But if you're
like,
dealing with a lot of angles that are moving, the cosine and sine become nicer.
but who looked at math and was like, you know what this needs? These things called trig functions. That's what this needs.
They had